Good afternoon, guys. Today our topic is frequency domain response of continuous time signal. Okay, so let's start. Guys, we know frequency means frequency. It means that is if we denoted it one cycle per time. Okay, say this cycle take 1 second. So this is frequency is 1 hertz. But up to this we know. Okay, but what do you mean by the frequency domain or frequency domain representation, time domain representation? Say say some, for the signal analysis we need some domain. We have to some clear idea. Say I am saying that welcome. Okay, so say if I represent it in the time domain, you can see welcome, this word I am taking say 2 second. Okay, 2 second you can represent it in this time. Okay, but in your frequency domain, you have to represent just like this. Okay, this is your frequency domain. So say there is a static signal that is called
Sir,
DC signal. Yes.
sir, please repeat once again, sir. Frequency domains.
Okay, frequency domain and your time domain. Look, we know that is f equal to 1 cycle per t. Okay, cycle per second or cycle per time. Okay, time is time period. That is called frequency. And whatever we represent up to this, we are doing in your normal work, that is a time domain. Because x-axis we are applying, that is x-axis, that is time domain, and as per time what will be the response. But in frequency domain, this x-axis is converted into your frequency. Okay, so that is called the frequency domain. One by one I will give you some example. So what is the needs of frequency domain, why we study frequency domain, then we will go for our Fourier series and Fourier series transform. Okay, so say I am saying welcome. This welcome taking this 2 second. Okay, so if you plot this for the time domain, then you can get this is the welcome. Okay, this is your time plotting. But in frequency domain, you can see this is only take some frequencies, that this frequency are occupied. That's why they are taking some frequencies. This is the frequency domain representation, and this is the time domain representation. Okay, say someone is playing some slow song. If you slow song, then you can see only few frequency are getting this. Just like welcome, I am saying welcome. If I say in this way, then if you go for your any display device, then you can analyze this. This type of signal will be coming. But if I told you welcome, 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 in this way, then you can get some sharp frequencies, some high frequencies. Is this is the some high frequency range. Okay, this occupies this much amount of frequency band. Okay, because within this time 2 second I told just three times welcome, 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 welcome. Okay, so that's why this is occupied more bandwidth. Okay, and if I say that welcome, then within this 2 second you can see only only one cycle is completed. Okay, because I told you one welcome, but in your previous cases, I told you within this time period at least three times welcome, welcome, welcome. So if you go for any oscilloscope, then you can find the high frequency or the if you say your first song, then you can get this type of frequency domain bandwidth. And for your slow song, or whenever I uttered a slow welcome only one time, then you get this type of signal. Okay, so this is the difference between the faster signal and slower signal in your frequency domain. But what happens in your time domain, if I told that is welcome, welcome, that's 2 second one time. But if I told welcome, 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 look, in this 2 second you can find this welcome, 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 three time you can get. Okay, so in this way we can differentiate a frequency domain and signal, a time domain signal. So our topic is frequency domain signal. So I think you can understand what are the frequency domain, and just basic part, then I will go for one by one. Say, if up to this it is clear, then I am going for the another a real thing. So why we need this frequency domain analysis, why we study for the frequency domain analysis is our frequency domain representation. Say, normal word, say there is a music composition. Say there is a music composition, some vocal is coming. This is someone is singing, someone is singing. Okay, but his singing is gain with a a1. Okay, means whatever the its amplitude, it will multiply with this gain. Okay, because in our volume knob, we are just whenever increase it, then our sound became high, louder. Okay, not faster. Just remember, louder and the faster are the difference. Okay, so this is the gain is x, gain in a1, and say this is the x1 signal. Okay, and it is coming, and there is a some keyboard. There is some keyboard. Someone is playing this. Say this is a x2 signal, x2t. This is x1t, because it is a time domain signal, and this is gain is say this gain is a2, and this is coming to the mixer, and someone is playing some flute. Okay, then say the gain is, this gain is a3, and the signal is x3t. So whenever we get this mixture, then we get a complete song, that is yt. So how could I represent this in our signal system? Say yt is yt is a1, because this is a gain is multiplied with this signal. So a1 is x1t. Just remember, this is the amplitude multiplication. Okay, your signal is original signal is x1, but if we multiply it with this amplitude, means something is integer, that will be your amplitude will be increased. So this amplitude multiplication is a1 is your gain. In your music system, you are, whenever you just increase your volume, then you just you move your knob. This is your gain. And then just like this is a2 x2 a2 x2t plus a3 x3t. Okay, this is your complete signal. You remember this. Here we are saying this is, if we represent it within 3, actually this is a time scaling. Actually this is a time scaling. So within this period is one cycle taking very less time. Within this two, I want to say that within this 2 second we are putting 3 signals. Welcome, welcome, welcome. Okay, very fast. But actually if I want to know what is the frequency, frequency is just one cycle completed per uh, per second, or the this is hard, one cycle completed in this time period. This is very less. This is this time of, so this is 1.3 second, or zero point 0.7 second. Because if you know, if I divided this 2 by 3, we can get something zero point 0.7 or zero point 0.6. So this is zero point 0.7 second, just like this. So frequency is very, very less. Okay, so up to this I think it is clear. Say, but in your time domain, this continuous signal is going on. This is continuous signal is going on. Okay, but in your time domain, if there is some noise, say this is a vocal, some speaker is uh, this speaker is singing some song. Behind it, a cat is a cat or dog is just barking. A, say this dog is just just creating some sound with this vocal. Okay, so another sound that is coming, that is coming xnt. Say this is a noise sound, this is a noise. Okay, because we don't want this dog sound, or some creature creating some sound or something. This sound is coming from unwanted sound, this is called the noise sound. But it is mixing with this sound.
Sir,
Yes, yes,
sir, I wanted to ask something, sir.
yes, yes, tell me.
Sir, it is far not in this topic, sir. But I had a doubt in, sir, data transmission, sir.
Okay.
During data transmission process, sir,
Hmm.
there is what is referred to as noise, sir.
What is referred to noise means, data transmission noise is also mingled with this noise, but after the receiving end, this noise was filtered. In data transmission line, there some noise is included with this data transmission. But after filtering, it will band pass filter, low pass filter, high pass filter. There is so many filters are there. Just like your TV, if you remember your TV set, there is a dish antenna. Okay, I think you get it. Dish antenna. Here is something is there. This type of things is there in your dish
Yes, sir.
antenna.
Yes.
Something, a torch like, a cup like, this types of things is there. Do you know what is this? This is actually a combination of filter, because various type of noise signal it is coming, and also the working signal also coming, but it is only taking, it is here it is filtering almost required signal, uh, and don't allow the noise signal. Again, whenever it is coming to the set-top box, here also in a TV channel there is an also a panel. Here also some filter is there. It is also neglect the noise signal and taking only required digital signal. But in your analog TV set system, whenever this TV, this antenna was coming before it, then you can see something whenever when an antenna, this type of antenna was there, something if it is moving or something, whenever storm is coming, your picture was just scattering. Okay, because this is the one kind of noise. I Is that clear? So there is a
Yes, sir.
is
Yes, sir, sir.
there is a so many filters are there. I am just talking about this filter. I am just talking about this filter. So someone somewhere this type of device was covered by another cup. Okay, but don't do this, because actually this signal is coming here, then it is reflected to here, then here some filter is there, it is almost filtering noise signal, then again it is filtered over there. Okay, and your data transmission in two types. This is also, you can consider TV, radio. This is a one type of data message, or your computer signal. There is a modem. Okay, there is a modem. So this data was coded and decoded and coded. So whenever unwanted signal or unwanted message was coming, this was coded and decoded. So only wanted message was taken and unwanted message was declined. Okay,
Okay, sir. Thank you, sir.
okay, welcome. Just let me remove this. Okay, so this is your noise. Okay, so whenever we go for represent this noise signal also, then we have to consider this. Then ut a1, you can know, this is x in t plus x1, this original signal, and it was mixed up because noise signal also coming from this from this loudspeaker, from the speaker, say A2 X2T plus A3 X3T. Okay, up to this you can understand this noise signal is coming and it is mixed up with this original signal. So what we'll do, if it is a time domain signal, you can do just reduce or increase this is gain. You can reduce this gain up to zero. If you reduce this gain up to zero, then total voice became closed. No one can listen this person uh, sing, singing. Okay, so you can't make it zero, otherwise this noise was coming. But in your frequency domain signal, you can see in your time domain there is a only continuous time. Within this xn, within this noise signal xn also there, within this within this your x1 also there. Okay, but if it is a frequency domain signal, whenever this speaker is singing or singer is singing, then this is the voice signal. Okay, because it is occupying this voice signal. Okay, and the dog is barking or something is creating noise, is just like uh, something sound is coming. It is coming just like this. It is coming just like this. Some, because it is, say, okay, so in this way, this is the noise signal is coming. Just like this sound is coming. So this is a discrete type or sometime periodic signal is coming, because it is continuing saying. It is occupying this band of this frequency. Okay, because frequency band are different. Now, if we apply some filter over this frequency domain signal, we can just take this signal, because we can filter this band to this band signal. We can take this and we can discard this type of signal or other signal, because we know the speaker. If we uh, measure it clearly, then we know uh, this speaker can speak only within this band limit. So we only take this band limit, we reject this this type of band, this type of signal. So in your frequency domain, you can see this is very much useful to reject your unwanted band, and filtering process is much uh, very much fruitful. So that's why we are very much interested to in data transmission and another things of this frequency domain response, because frequency, whenever we are data transmission occurred, then frequency domain response gives us good filtering process, whereas the time domain process is uh, not efficient to remove this noise. Not only noise, the handling within this band limit, we have different sounds also it may be transferred within same time. But if I want to transmit in the time domain, look, different signal are coming, but it will just mixed up. We don't separate it. Okay, so that's why we are very much interested and required to know about this frequency domain representation and frequency domain of the of any signal. I think uh, it is clear to all of you. If you have any question, then you may ask me. Now, so we know there is a frequency domain signal or the continuous signal. Uh, this continuous signal xt, whenever it is transformed into frequency domain, then it is converted into omega. Okay. So if it is a periodic signal, if it is a periodic signal, then we can represent it in Fourier series. If this is a non-periodic signal or aperiodic signal, then we can make it Fourier transform. Okay. So what is Fourier series, Fourier transform, etc.? Actually, scientist Fourier, uh, he observed whenever he is working, he was working on heat transmission. Then he observed a any periodic signal which may be sine wave or not sine wave, not sinusoidal, it may be converted into infinite time summation of sine signal or cosine signal. So this is the Fourier theorem.
Sir,
Yes, yes, tell
sir,
me.
please repeat the line, sir. Please repeat the line.
Okay, I write down this. Actually, scientist Fourier, he observed when he was working on heat transmission analysis, then he observed if any periodic signal, first you have to mention that is any periodic signal, it is converted into a infinitesimal summation, matlab in summation of infinite time, sine wave and cosine wave. Okay, get it? If say this is a periodic signal, one by one I give you some all example. This is a periodic signal, this is not a sine wave, is that a sine wave, this is a square wave. Okay, here is not square but it is a square wave, but you can convert it into a into infinite time summation of any sinusoidal signal, but its fundamental frequency should be fundamental harmonics should be same. Look, in this way, this you can represent in this way, so this is called first harmonic. If, because summation of infinite time, okay, so infinite time means if you apply this, so this is two harmonics, the summation of two harmonics, because if you two add two harmonics, then you can get this. If this is a three, then you can, this is a three harmonics. In this way it was represented by scientist Fourier. Just I write down these things. A non-sinusoidal, periodic, okay, periodic function can be expressed as an infinite sum of sinusoidal function. Sinusoidal function. Okay. Uh, could you get this? A non-sinusoidal periodic function can be expressed as an infinite sum of sinusoidal function. Okay, this is the Fourier function. Just explain this so that you can understand. Look, this is a square wave. Okay, this is a square wave. Now, this is a square wave. This is not a sinusoidal function, but this is a periodic. Periodic means after a certain period, it is repeated. That's why this is periodic. So, so this is a time period is t equal to 2 pi by omega 0, omega naught. This omega is the frequency. And now, if I apply some, look, sorry, this is, look, this signal, this is, you can say this is sine omega 0 or omega naught and t. This is first time. So this is called first harmonic. First harmonic. Okay. So you can represent this signal in this way also. Okay. If there is another signal which is completed two times, two cycle, okay, say this is this is two times, so you can say this is sine 2 omega 0 t. This is a second harmonic. This is called second harmonic. Okay, I think from this picture you can clear your idea regarding harmonics. What is harmonics? Now, if there is a three signals, three cycle, not signals, three cycles is there within this period. One, this is two, this is three. Okay, you can see there is the third harmonic. So this is sine 3 omega 0 t, omega naught t. So this is called third harmonic. Okay, so this squares wave, as per the Fourier series, this square wave could be represented in this sinusoidal signal. Okay, that is, but it is a infinite time summation of these harmonics. Means you can do this by one, you can do this by two, you can do this by three, you can go for four, five, six, seven, eight infinite time harmonics. So this is called the Fourier series. Okay, so signal this signal can be represented into a Fourier series with fundamental frequency omega 0. Look, this 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 signal is represented in Fourier series by this fundamental frequency, that is omega 0. Okay, this is the main statement of Fourier series. Any non-sinusoidal periodic function can be expressed in infinite sum of sinusoidal function. Later on, I am going one by one. I am going to going into this deep. Look, Fourier series can be represented in two ways. First one is complex exponential, and another one is a trigonometric expression. In trigonometric expression, you can directly find the sine and cos a0 summation of then b1 cos b1 sorry a1 cos a1 sine omega 0 t b1 sine omega 0 t in this way. And another is complex conjugate means e to the power j theta. Okay, say first harmonic, it is represented e, e j omega naught 0. The second e j 2 omega naught 0. This is the second harmonics representation. And third harmonics is E j 3 omega naught t. Okay, in this way we can represent each signal, and here we can write down, that is, any signal can be represented in this way infinite time summation. Means k, if I put k is minus infinity to plus infinity, then a k, this is a coefficient, and e to the power j k omega naught t. Look, whenever the first harmonics, that is k equal to 1, whenever second harmonic k equal to 2, whenever third harmonic k equal to 3. So infinite time, this k is summation is minus infinity to plus infinity. You can do anything. Okay, you can take 5 harmonics, you can take 1 harmonics, you can take 13 harmonics, whatever may be, but fundamental frequency should be same. Fundamental frequency should be same. Then you can represent any signal into any periodic signal into a sinusoidal signal. Okay, so this is the Fourier statement. Guys, time is very less. Please join for the next class. Just same link. Just I am stop here and again join this within 1 minute, please.